So in this first part of the experiment, you've got three pieces of equipment. You've got a big piece of foam, and you've also got a picket fence object, which is just a clear piece of plastic that has black stripes on it. You've also got this photogate. So a photogate is a device that puts out a little beam of infrared light, and then it's got a detector on the other side. So a computer can tell when the beam is blocked. It's infrared light, so you can't see anything, but the computer can. So what we're going to do is we want to measure the acceleration of an object in free fall. So you take your piece of foam and put it on the ground so that the picket fence is not going to shatter when you drop it. And then you're going to take a computer program, which I will show you on screen in a moment, and you would start the program running, and then you're just going to drop the picket fence through the photogate in such a way that those black stripes are going to block this beam here. So that's all you'll do, is you'll start the program running, and then you just drop the picket fence through the photogate. So now I'm going to show you the program. So you open up the Physics 1100 folder on the desktop, and you want the freefall program this week. So now I've shown you how to physically do the freefall experiment, and now I'm going to show you the program that we use. So to begin with, I want to warn you that this program is a little more complicated than it should be, but it does what we need it to. So first of all, just a warning that it may be called picket fence rather than freefall, but either way, it's the same program. Now there's a couple of things that we need to change before we can take data with this program. So up here in the corner, you'll see a setting that says intervals to time. What is that? On your picket fence, the intervals are the spaces between the black lines, so one interval between two lines. So we want to count up the clear plastic regions between the black lines. So 1, 2, 3, 4, 5, 6 intervals on my picket fence. Yours may be different, so do count it up when you get it. But you're counting the clear plastic regions between the black lines. So I've got 6 of them, which means I need to change this setting from 10 down to 6. The second thing we need is the edge-to-edge distance or angle. So what is that? Well, again, on your picket fence, the edge-to-edge distance is from the front edge of one black stripe to the front edge of the next one. So leading edge to leading edge. You want that distance. So grab a ruler, and on my picket fence, that looks like it's about 5 centimeters. And that's the value we want to put here, but it needs to be converted into meters. So this quantity does need to be in meters. So 5 centimeters would be 0.05 meters is equal to 5 centimeters. So now I'm ready to take my data, and what I'll do is I'll first trigger the program, and then it'll wait for data, so which means I can then drop my picket fence through the photogate. So the way that you trigger it to start waiting for data is up here in the corner, there's this little white arrow. If you happen to see a second button with 2 white arrows on it, don't click that. We want the button that has a single white arrow on it. So I click that, and now the program is waiting for data, which means I would take my photogate, and I've already got my cushion down below, and I just drop the picket fence through there. And now I have my data. So it's showing me a distance time graph right now, and that's great, but we'd like to look at a velocity time graph because we're measuring the acceleration of that picket fence, and we expect the slope of our velocity time graph to be nice and linear and to be equal to the acceleration due to gravity. So down here in this corner, there's a little button that actually switches you between those two graphs. So if I click it once, I go to the velocity time graph. If I click it again, I go back to the distance time graph. One slightly glitchy thing to be aware of is you notice how in the middle of this button there's a double-headed arrow. If you click on that double-headed arrow, nothing happens. But if you click literally anywhere else on the button, it works the way it's supposed to. So just be aware of that slightly glitchy thing. Avoid the double-headed arrow when you click. So we get onto the velocity time graph. We double-check that it looks nice and linear, and it basically does. And then we want the slope of that, which would be the acceleration. And that's just given to you right here. So they give you the acceleration in meters per second squared, and that's the value that you're going to compare to the known value, 9.81, to see whether they agree within the limits of uncertainty. If for any reason you decide you want to retake your data, the way you do that is you hit cancel, this button down here, and that gives you back this white arrow in the corner. And then you can press the white arrow, and you can take new data if you want to. So in this experiment, for the first time, you will write a conclusion. Most of the experiments we do this semester have you write a conclusion, and in fact, this experiment has you write 2 of them. So this is the first one, question 4. And for the first part of the semester, they do give you this bullet list of things that you need to put in your conclusion. So I'm going to go through each of these with you. In the first item, they tell you to state the objective of the experiment and the hypothesis. So the objective is, what were you trying to measure? What were you trying to accomplish here? So for example, for the free fall experiment, your objective was that you were trying to measure the acceleration due to gravity near the surface of the Earth. For the hypothesis, it's usually a variation on, we're expecting to see that the measured value we got agrees with the theoretical prediction for the value. So again, for the free fall experiment, this would be that we're expecting our measured value to agree with 9.81, the theoretical acceleration due to gravity. So you're just trying to say those two things in a full sentence here. The second item says state your values, so both the measured value and the predicted value, and you need to put units and uncertainties on them. So in this case, you'd just write down your two values in a full sentence. The next item is that you would state your percent difference between the two values, so between your measured and your theoretical values. So by the time you get to here, you've already calculated this value, so you would just write it down in a full sentence. The next item is state whether your values agree within uncertainty. So this one's a little bit trickier. So how do you determine whether your values agree with an uncertainty? Well, first of all, say you've got these two values, the theoretical value, 9.81 plus or minus 0%, and an experimental value that you got from the computer program. And let's say that that was 10 meters per second squared, plus or minus 3%. And not only do you have those values, but you've also already calculated the percent difference between them, which is this, 1.9%. So, do your two values agree with an uncertainty? The way in which you determine that is first you find the sum of your uncertainties. So 0% for the theoretical value plus 3% for the experimental value gives you a total uncertainty of 3%. Now that's the maximum amount of deviation between our values that we're expecting to get based on the equipment we used. So whatever our values are, they're not supposed to differ from each other by more than 3%. The percent discrepancy that you calculated here, that's a measure of how far different your two values are. So your values agree within uncertainty if the percent difference is less than the sum of the uncertainties. So 3% is the maximum amount of deviation you expect to see, and if you only got 1.9% difference between them, that means your values agree within uncertainty. Now let's consider another case. Let's say that our experimental value wasn't 10 meters per second squared. It was 10.5 meters per second squared. But that changes what our percent difference winds up being. So now it's 7.1%. And that's bigger than the sum of the uncertainties. So now you'd have to say that the values disagree with an uncertainty because the percent difference, so how different your values are, is larger than the sum of the uncertainties, which again is the maximum amount of deviation we expect to see given the limitations of our equipment. And so that's what you would say when you come back here. You don't need to give any calculations here, just say it in a sentence. The next item says state whether the theory is supported by your data. So if your values agreed with an uncertainty, you'd say, yes, the theory was supported by my data, because your value agreed with the theoretical prediction within uncertainty. If they didn't agree, then here you would have to say the theory was not supported by your data. And finally, the last item says, identify and discuss what the largest source of uncertainty was. Now what your answer here is going to be different depending on what you answered to the previous questions. So it depends on whether your values agreed with an uncertainty or not. So if your values agreed within the limits of uncertainty, so your percent difference was smaller than the sum of the uncertainties, then your largest source of uncertainty is whatever measured value had the largest percent uncertainty. So in this first experiment, we've only got two uncertainties, 0% and 3%. 3% is bigger, so that's our largest source of uncertainty, and it was due to the photogate in the computer program. So that's what you would say in your conclusion. The largest source of uncertainty was the 3% due to the photogate in the computer program. However, if your values did not agree with an uncertainty, then your answer is going to be different. So if the percent difference is greater than the sum of the uncertainties, your values disagree with an uncertainty. So what's the largest source of uncertainty? Well, it can't be any of the uncertainties on the data, because we took those into account. It has to be something else. So then you and your group members would talk about this and try and figure out what could have caused it. So was it friction? Was it air resistance? Did you not level your track accurately? Maybe your projectile wasn't launched horizontally. You have to think about the experiment and try and identify the one thing you think that might have caused the discrepancy, and it'll be something other than the data values. And by the way, there's a second acronym here that they use that they didn't really define, VAWU. That stands for Values Agree Within Uncertainty. So that's how you write a conclusion, and you're going to write 2 of them for this week's experiment. So now you're ready to move on to the next part of the experiment, which is we're going to look at some simulations. So open up the Physics 1100 folder and go into the Lab 3 folder. And there's 3 simulations here. We're going to look at all 3 of these. So I'll open up the first one. And what this is that it's going to show us a little movie. We're going to click Run, and we can click Stop later. And it'll show us a little movie of these 2 balls. One of them will be dropped straight down and the other will be projected exactly horizontally, and you'll be able to see them both falling under gravity. So it looks like this. I click Run, both balls get projected or dropped, and then I can click Stop after they bounce, because I don't actually care about what happens after the first bounce. If you don't like the image on the screen for any reason, you can click Reset. But it does have this sort of glitchy thing where it doesn't erase the other stuff that's on the screen. So to erase everything, click Control-H, and that gets rid of all the stuff from the previous run. So again, you click Run to start it, and you stop it after the bounce. And it shows us both balls falling, as well as the X and Y components of their velocity. Now you will want to screen capture this and paste it into your report, so do that in the usual way. And then there's a few questions in the lab manual that you'll need to answer about the horizontal or the vertical velocities of the 2 balls. So answer those, and then you're ready to proceed to the next simulation. So you close this down with the X in the corner. If it asks you if you want to save changes, always say no. Then you open up the next simulation. And in this movie, the ball is going to be fired upwards at an angle, and then it'll fall back down to the ground. So again, you click Run, and go ahead and click Stop after the bounce. Now there's another little glitchy thing here in that it didn't show us the initial position of the ball. So one thing you can do is click Reset, and then it redraws it in there, and then this is a nicer picture for us to keep. So again, screen capture this and paste it into your report. After this, there's more questions for you to answer, like what happens to the velocity of the ball as it's rising, and what is true at the top of the trajectory. And it'll also ask you to come up with 2 to 3 conclusions about the velocity or the displacement or the time it took the ball to get to this end point here. So think about the symmetry of this situation. What's true about the horizontal or vertical velocities at the end of the motion relative to the beginning of the motion? Or what is true about the displacement of the ball at the end of the motion compared to the beginning? Or what's true about the time it took to get to here relative to, say, the midpoint? So just think about the symmetry of this, and as I said, you want to come up with 2 or 3 conclusions about what's true regarding the velocity or the displacement or the time when the ball gets to the end of its motion. Then you're ready to go on to the third simulation. So again, close this down, say no to the changes, and open your third simulation. And this one's very similar, except that the ball is going to go up in the air and then it's going to come down lower than it started, so lower than the launch height. So again, click Run, let it fall, and stop it when it bounces. And again, if you want this initial position, just click Reset and it draws it in for you. So as before, screen capture this and paste it into your report. And there's some more questions for you to answer, such as where is the speed of the ball greater than the launch speed? Where is it less than the launch speed? Where is it equal to the launch speed? Now, just so you know, you don't need any of the numbers off the screen to answer these questions. You should be able to do it based on the theory you've learned in class. So you can just answer with words. You don't need numbers here. And then you're done with the last simulation, and you can go on to the next part of the experiment. So in this part of the experiment, you're going to use a Hot Wheels car as a projectile. So you'll fire this off the edge of the desk, and then we're going to actually measure that horizontal range, so how far it goes horizontally from the edge of the desk. We're also going to calculate that quantity theoretically. So the point of this experiment, however, is to get that range. Now on your table, you've got a brick and a section of Hot Wheels track, and you should tape both ends of the track down. So one of them gets taped right to the edge of the table, the other gets taped to the top of your brick, and that makes a little ramp for your car to go down, like that. Do try and get this end of the track as horizontal as possible, since we are assuming in our calculations that the car leaves the table horizontally. In your lab manual, you've got a table and there's 4 quantities we're going to be measuring. So the first of them is the length of the car, so just how long it is from end to end. So you grab a ruler and measure that. The second thing we need is the height of the table, so how high up the car is when it leaves the edge of the table. So grab your meter stick and just measure that. The third thing you're going to need is what's called the photo gate time. So what's that? Well, over here we've set up a second photo gate, and it's set up in such a way that when the car comes out of here, it's going to block that photo gate beam as it's going past. So we're going to use that to measure the time that the photo gate was blocked for. And the reason why we want that is we actually want the velocity of the car as it's leaving the table. So velocity is distance divided by time, right? This distance divided by the time that we measure with this photo gate gives us the velocity of the car just as it's leaving the track. So what we really want is velocity, but to get that, we're going to need the time that the photo gate was blocked for. So distance divided by time gives you the velocity of this car just as he's leaving the table. On this timer, you want it to be in gate mode, so that's one click up on this selection toggle here. You also want it to be in read mode, which just means click this downward, the light will be on. And the way that sets things up is that this timer is going to run anytime the beam is blocked. So for example, if I put my hand in here, you can see it running. If I let go, it stops, and it's also set up that you can't trigger it twice. So if you need to take new data, a new data run, just click reset, that zeroes it, and again, it'll only run when the beam is actually blocked, and it won't run a second time. This number that you're reading is in seconds, so it's not in any weird units, these are just seconds, so 1.4180 seconds in this case. You use those three quantities, the length of the car, the height of the table, and the photo gate time, to calculate theoretically what the range of this car is supposed to be, so how far it goes horizontally from the end of the table. We're also going to measure that directly. So here's how you do that. You've got a piece of carbon paper on your desk, and what you're going to do is I recommend you run the car down the track, see where it lands on the floor, and then you're going to put this piece of paper there so that when the car runs the second time, it's going to make a mark on the page. So you tape the page down, and I recommend you also tape it down in such a way that you can still flip this part back. So you do a trial run with your car, see where it goes, and then you put your piece of carbon paper there, tape it down, and then when you run the car a second time, it's going to make a mark on the page. Now, one thing to be careful that you always do when you do a new run is to click this reset button here. So you zero the scale, you've got your page taped down, and you just project the car onto the carbon paper, and now you can get down on the floor, flip back the carbon paper, and use your meter stick to measure how far from the edge of the table the car went. So that's your measured range, your experimental value. You'll be comparing that to the value you got theoretically. So that's how you get all of your experimental values. And in the next part of the video, I'm going to show you the calculations that we do and point out a few things to be careful of. So now I'm going to talk about the equations that you use in this experiment. So the first thing you'll calculate is the launch speed of your Hot Wheels car. So how fast was it going when it left the track? And as I mentioned earlier, it's just going to be the length of the car divided by the time that the photo gate was blocked for. So velocity is equal to distance divided by time. The next thing you calculate is the time of flight. This is how long it's in the air for. The way we get this is, we know from theory that the time of flight, if you launch the car horizontally and just let it drop under gravity, is exactly the same as the time of flight would be if you dropped it from that same height. So we calculate that, and you have to be a little careful here in that d is equal to the height of the table here. So it's changed its definition relative to what it was up here. So up here d was the length of the car, down here d is the height of the table. So the time of flight is going to be 2 times the height of the table divided by the acceleration due to gravity, all square rooted. Once you've got those two quantities, you can then calculate the horizontal range. So this is our theoretical horizontal range. This is how far we figure the car is going to go. Again, d changes its definition, so it's something to be a little careful of when you're doing the calculations. Over here, d was the length of the car. Down here, d was the height of the table, and over here, d is the horizontal range. But this horizontal range is simply going to be v times t. So after you've gotten these quantities, you're also going to have uncertainties that you've calculated for all of them, and then you proceed to something that's going to
become very familiar over the course of the semester. And that is, once you've got your values, you summarize them in a table. So you'd write down your values here with their units, plus or minus their percent uncertainties, and you put a title on the table, that's worth marks. And then next, you would calculate a percent difference between your two values. So you compare those two, calculate a percent difference. And once you've got that, you could then proceed on to write up your conclusion. So remember that your conclusion consists of answering all of these points in your bullet list. So state the objective, what were you trying to measure? In this case, it was the horizontal range of the car. What's the hypothesis? Basically that the measured value is going to agree with an uncertainty with the value that we calculated. State the measured values and the predicted values with their uncertainties in units. State your percent difference that you just calculated, and then say whether your values agree with an uncertainty. So is your percent difference smaller than the sum of the two uncertainties? State whether the theory is supported by your data, and then finally you identify what your largest source of uncertainty is. And you identify a largest source of uncertainty regardless of whether your values do or do not agree with an uncertainty. If the values do agree with an uncertainty, then your largest source of uncertainty will be something you took into account. So you go and look at your raw data values. Whichever measurement you took had the largest percent uncertainty, that would be your largest source of uncertainty when the values agree with an uncertainty. If the values do not agree with an uncertainty, then the largest source of uncertainty has to be something you didn't take into account. So something like friction or air resistance, or maybe the track wobbled or something. In general, pick one thing. Choose the one thing you think is most likely to be your largest source of uncertainty.